it. Here I show a very a cartoonish representation of a magnetic heat pump prototype would look like. And what I want you to know is that the most key component over here is this regenerator. And this regenerator is made entirely of the magnetocaloric material. And so the working fluid here shuttles heat within this magnetocaloric material and the regenerator fluid to create a temperature span, and it provides cooling. And so what we do is we put it in a thermodynamic cycle, which is called the active magnetic regenerator cycle. It has 4 steps to it. So in step 1, you magnetize the bed. It raises the regenerator's temperature by, say, a certain delta T. We have a heat transfer fluid that flows through it. It goes from the cold end to the hot end, so it carries the heat away. And as it does so, it forms a temperature gradient. You remove the heat by demagnetizing the material system. The material then cools down by an equivalent amount of delta T. You have fluid flowing through it again. It goes from the hot end to the cold end instead, brings the regenerator back to room temperature, and then strengthens the gradient. And the cycle happens again and again and again. So with this context and background in mind, let's look at all the characteristics that the perfect magnetocaloric material needs to have in a perfect world. So first and foremost, it should definitely show a large magnetocaloric response at a moderate magnetic field. You don't want to put a really high magnetic field, which would wipe out your credit card every time you walk past it. Figures of merit of a magnetocaloric material are the adiabatic delta temperature change, of course, which is delta T adiabatic. It's associated with a magnetic entropy change, which is kind of directly proportional. Not important here how the physics of it works. I will be showing later some curves of delta S. So just an important point to keep in mind is higher the delta T, higher will be the delta S. And then, of course, there is the reversible transfer of heat as the magnetocaloric material is exchanging energy, heat exchange fluid, which is water in this case. It should, of course, be made of geo-abundant elemental constituents that have no supply chain complexities associated with it. It should have high thermal conductivity, low heat capacity, so it doesn't itself get heated up, but just transfers the heat to the water. High electrical resistivity because it's being subjected to a continuous changing magnetic flux. You don't want too much eddy current loss. It should be mechanically strong and, of course, chemically stable. Corrosion resistance is always in contact with the heat exchange fluid. And so since room temperature magnetocalorics have been discovered, it's been around 30 years. And there have been many materials that have been explored to see what is the best magnetocaloric material out there. So here's an example from a very recent publication by Oliver Goodfleisch's group in Germany. And you can see over here what it does is it captures approximately near room temperature what are the most promising magnetocaloric materials. So you have to look at around near 300 Kelvin, which is room temperature. And you can see over here that the best magnetocaloric material is, of course, at an applied field of 2 Tesla, iron, rhodium. I've done a lot of work in the past with iron, rhodium. Excellent system when you look at it, extremely expensive. And so rhodium is a critical material. You don't want to make anything, a regenerator with iron, rhodium. We also have in the room temperature range here manganese iron phosphides, and the initial ones versions of this compound also had arsenic in it. Toxic, don't want to use this. We have our Heusler alloys as well as the oxides, perovskite oxides perfectly. They also work at room temperature, but they have a rather low delta T. And then right over here, we can see we have gadolinium and the lanthanum iron silicides. Now, gadolinium is a rare earth element. Again, it's not critical yet in terms of supply chain, but it is expensive. Our best bet as of now, and it's kind of universally agreed in the magnetocaloric material, are the lanthanum iron silicides, especially that doped with hydrogen. And so they they work for all practical purposes. They tick all the boxes that makes a good magnetocaloric material, including the reversible transfer of heat. So it's got good thermal properties as well. The only problem here is that lanthanum iron silicides are brittle and they are not quite easy to shape. So, for a good magnetic regenerator, to improve the efficiency of the device, you need to manufacture the heat exchanger. That is, the regenerator here is the heat exchanger with customized architectures. Even now, most of the prototypes that are out there, and they're made up of either packed particle beds or plain plates, and each of them have its own inherent challenges in terms of despite good when you deploy it in a device. So packed beds, for instance, they segregate, leading to pressure drop along the length. And in extreme cases, it can also lead to flushing of the particles in the surrounding heat exchange media. Stacked plates are essentially composites, so they are made up of the magnetocaloric material bound together with epoxy. And so they also have very strict geometric requirements, like the plate thickness of less than 500 micrometers, spaced 100 micrometers apart. And it doesn't really work that well. It's really hard to make. They show dilute caloric response because of the presence of a binder. And so the community is still looking for solutions. And there are theoretical papers that show that if you make microchannels or if you make materials with pin fin arrays, they would demonstrate a higher capacity than parallel plate regenerators.